Thanks for tuning into this Revision Zone Maths video. In this video, we're going to be looking at lots of examples of how to use the quotient rule. So let's start with example 1. We're given a function, f of x is equal to 2x plus 5 over x cubed, and we have to differentiate it. So of course, we've got to say at the beginning that x cannot actually be 0, because if x is 0, then the denominator becomes 0, and we run into problems. So with that caveat out the way, let's look at a solution. Since we want to use the quotient rule, because we of course have a quotient here, there's some function on the top divided by some function on the bottom, what we actually say is we define our capital F to be lowercase f over lowercase g in Newton's notation, where we can say our lowercase f is indeed just 2x plus 5, and our lowercase g can just be x cubed. So once we have that, we turn to the formula for the quotient rule, which tells us to be able to differentiate capital F, I start with my g, so I write down my g first, and then I differentiate the top function, so I write down the derivative of f of x, then I subtract, and then I write down my top function again, so I write down f of x, then I differentiate my bottom function, g, so we differentiate g, and finally we're going to have the fraction line with the denominator g actually squared. This is our quotient rule formula. So to be able to use this formula, I of course need the derivative of f and the derivative of g. So I'm going to go to my description of f and g and write down those derivatives. So f prime would work out to be nothing else but 2, because 2x differentiates to give me 2 and 5 differentiates to give me 0. And x cubed differentiates to give me 3x squared. Okay, so now it's just a matter of putting all this in. So we're going to put our g in first. Our g is of course just x cubed, so I'm going to have an x cubed on the top. And then my f prime, we've just worked that out, that's just 2, so I'm going to write the 2 down. And then we have a subtraction sign, so I'm going to copy the subtraction sign down. After that, we have the f of x, so I'm just going to copy my f of x down, which is 2x plus 5. I'll write that in brackets to make sure there's no confusion. And then for the last term on the numerator, I'm going to have g differentiated. So g prime is of course 3x squared as we worked out. So I'm going to write down times by 3x squared. And that gives us all of the numerator, and the denominator we can just write down the function g all squared. So I'm going to have x cubed all squared. Now the only thing that's left here is to simplify this. So the first term becomes 2x cubed. I can expand the bracket I have here with the 3x squared, so I'm going to get 3 times 2 to give me obviously 6x cubed, and then the 3 times 5 is going to give me the 15, and then the x squared is just there, and the denominator would at this stage become x to the 6 by standard rules of indices. And finally we can sort of tidy this up a little bit further. Perhaps I'll write this on sort of slightly left side, given that there's so much space on this side of the screen. So I'm just going to have 2x cubed minus 6x cubed minus, should have been 15 here. I don't know why I wrote down a 5. Minus 15x squared, and the whole thing is over x to the 6, which we can of course collect sort of coefficients and say it's going to be minus 4x cubed minus 15x squared all over x to the 6. We can take the minus out entirely and say it's going to be 4x cubed plus 15x squared all over x to the 6. And of course we can tidy this up a little bit further by factorizing out an x squared to have here, and then the x to the 6 is still in the denominator. But of course we're going to have some cancellations, because the x squared is going to cancel with x to the 6, so perhaps I can just get rid of that and change the power of that 6 to a 4. So we've basically been able to work out our answer. I'm slightly hesitant to put that line there because it looks like it's part of the fraction, so I won't do that. Now let's do a very quick check, which we should be able to squeeze in at the bottom here. So the check, what are we going to have? We're going to have, well, let's just do this directly. So we've got our function f of x, and we know it's equal to 2x plus 5 over x cubed. We can split the fraction up to say 2x over x cubed plus 5 over x cubed. But then that's the same thing as 2x to the minus 2 plus 5x to the minus 3. So we can now differentiate this term by term fairly directly using the rules that we already know. So we're going to get minus 4x to the minus 3, and we're going to get minus 15x to the minus 4, which of course we can sort of tidy up slightly further. If I write that here, it's going to be minus 4 over x cubed minus 15 over x to the 4. So perhaps if I get a common denominator and take the minus out, it's not surprising that I'm going to end up with this, which is exactly what we got for the first part. So the next example is also a fairly standard sort of a quotient function. So let's work out its derivative. In this case, we'll try and work in Leibniz notation, just so we have fluency between sort of Leibniz and Newton's notation. So I'm going to write my function y as a function of u and a function of v. But of course, to make this quotient work, I've got to choose my u to be x plus 1, and I've got to choose my v to be x, right? So I say where u is x plus 1 and v is x. Of course, needless to say, because v cannot be 0 as a function, then I can't take x to be 0. So that is explicitly ruled out above. So what's the quotient rule formula? Well, again, like last time, we start with v and we end with v. Okay, so I'm going to write down v, then I'm going to differentiate my u, then I'm going to take away my u, and I'm going to differentiate my v, and then I'm going to end with the square of v. So this is the quotient rule formula in Leibniz notation. So again, I need both the derivative of u and the derivative of v. So I go to my u and I say, what's the derivative of u with respect to x? That's a standard polynomial. I'm just going to get 1 as a derivative. And then I say, well, what's the derivative of v with respect to x? That's again a standard polynomial, so I'm just going to get 1 as a derivative in that case too. So now I come back to this formula and I start to make substitutions. So perhaps I can just sort of do that here. So what's my v? My v is just x. What's my du by dx? That's just 1. What's my u? Well, that's x plus 1. What's my dv by dx? Well, that's just 1. And then what's my v? Well, that's just x, but I'm going to square that because the denominator is v squared. Now, it's just a matter of tidying this up. So the numerator gives me x minus x plus 1, and the denominator gives me x squared, which of course, if I expand out the bracket, I end up with that. And unsurprisingly, what we actually have is we have these x's cancelling. So since the x's are going to cancel, then I can say my dy by dx, which perhaps I can write here, is just left as being minus 1 over x squared, and we've worked out our derivative. So let's do a quick check. So how else could we have done this? Well, we could have gone back to our old way of thinking, which is to get this in a form where we can differentiate each term by using another rule. So we could split this up as actually a fraction, like so, and then the x over x is going to give me 1, and then the 1 over x is x to the minus 1. Of course, while I do all of this, I should note that x cannot actually be 0, because otherwise the thing that I start with is not quite defined, and then these steps are going to start to cause problems as well, right? But anyway, getting back to where we were, now that we have our function in a form that we can actually differentiate quite well, then we just differentiate each term. So what's the derivative of 1? Well, that's just a number, and the derivative of a number or a constant function is always 0. And the other one is, again, a standard polynomial type function, so we multiply by the power and we subtract 1 on the power. So we end up with minus 1 over x squared again, because the x to the minus 2 can be expressed as 1 over x squared when you undo the index form, but there's a minus 1 already, so it's going to be minus 1 over x squared. And again, in both these cases, we see we actually have the exact same answer. So that's a fairly standard application of the quotient rule again. Again, the key idea being that provided you can write a function as a quotient and you can differentiate each part of that quotient, then you can use the quotient rule to differentiate the overall function. So example three is another function. In fact, it's the pretty much very much like the first example we looked at, but now we've swapped the numerator and the denominator from that example to be able to get this example. This has been done for a particular purpose, and you'll see this as the example progresses. So let's work out the derivative, and again we're going to switch back to sort of Newtonian notation just to develop fluency. So I'm going to write my capital F as a function lowercase f over lowercase g, where of course I've got to choose my lowercase f and my lowercase g in a sensible way. And it's fairly obvious I'm going to take my lowercase f to be the numerator and my lowercase g to be the denominator. So my f lowercase is x cubed and my g lowercase is 2x plus 5. Should have mentioned this. Of course, the function capital F is not defined for when the denominator is 0, sorry, which means 2x plus 5 cannot be 0. Okay, so that's just a technicality we've got to be aware of. But let's get back to the differentiating the actual thing. So the quotient rule, I'm just going to write it down. It starts with the denominator, and then I'm going to end up with the denominator as well at the end, right? Because quotients are special because there's a denominator. That's what makes them a quotient. If there is no denominator, it's not really a quotient, and it's obvious that in the actual formula for the quotient rule, it's the denominator that plays a crucial part. As long as you keep track of where the denominator is going to go, you can work the formula out without really having to do too much thinking. So once we've written that, let's differentiate f because we're going to need to know derivatives of f and derivatives of g. Since we have f and g, we can just differentiate these directly. So my f is going to differentiate to give me 3x squared, and my g is going to differentiate to give me 2 because 2x differentiates to give me 2, and 5 differentiates to give me 0. So now let's substitute into the formula the quotient rule formula, the actual sort of expressions we've worked out. So my g is 2x plus 5, so let's write that down, 2x plus 5, and my f prime is 3x squared, so let's write that down, so times by 3x squared. My negative sign has to come, so I'm going to put the negative sign down, and then my f has to come, but my f is just x cubed, so we write that down. And then my g prime has to come, but I have my g prime right here, so I'm going to write that down, so that's 2. And then my denominator is just going to be g squared. So I have my g here, 2x plus 5, I'm just going to square the whole thing. So I'm going to say 2x plus 5, the whole thing squared. So now we have to just keep our wits about us and tidy this up without sort of making a mistake. So let's try and do that. The first sort of thing here is going to expand out to give me 6x cubed plus 15x squared. So it's going to give me 6x cubed plus 15x squared. So now that we have that, the remaining term in the numerator is just 2x cubed. So we can now combine the numerator quite nicely. The denominator I'm just going to leave as 2x plus 5 all squared. I don't really need to expand that any further. So the 6 and the negative 2 are going to combine because I've got the same sort of term there. I've got x cubed there and x cubed there. So I'm going to get 4x cubed, and then the plus 15x squared is just going to remain. Okay, so we've actually managed to work out our derivative for the quotient that we started with, but of course all of this is only true for when 2x plus 5 is not actually 0, which in other words x is not actually minus 5 over 2. So I'll just write that as emphasis on the side. Remark, we cannot easily check. We cannot easily check our answer directly. So what I mean by that is, in the previous example, when we actually had, so let me say here, previously, which is example 1, example 1, what we actually had as our function was 2x plus 5 over x cubed, right? So the same thing as what I have here, but obviously flipped. But in that case, we could have expanded this, or rather used some algebra to be able to express this in a form where we could get terms like the ones I'm writing down now, right? Which then can be written in sort of standard form, and we can then go on and differentiate each term and check, right? But in this case, we cannot do that because there's only one term in the numerator, so it makes no sense to be able to expand the numerator into lots of other terms, okay? So in fact, this example is a perfect case of why we need the quotient rule, because without the quotient rule, a function like that, we would be completely hopelessly stuck with this as to what to do. So example 4 has a lovely function that we need to differentiate. And again, you might notice that this is basically the same as what we did for example 2, but the numerator and denominator have been swapped again. Again, we've done this to try and make a point, and hopefully you'll see that point as we work through this. So let's do this in Leibniz notation, keeping with our convention. So we can write y as a function of u over v, where our u is going to be the numerator x, and our v is going to be the denominator x plus 1. Of course, as before, because the denominator cannot be 0, otherwise the function is not defined, x cannot actually be negative 1. So any of the working I do does not apply for x equals negative 1. Okay, so let's write down the quotient rule, and again we're going to start with v, and we're gonna basically end with v. Okay, so we've written down our quotient rule. So I need my du by dx and dv by dx. So let's work them out. So my du by dx is basically going to be 1, and my dv by dx is basically also going to be 1, because x differentiates to give me 1, and x plus 1 also differentiates to give me 1. In other words, the line y equals x and y equals x plus 1 are parallel, right? So they're going to have the exact same gradient. So once we have that, now it's just a matter of going back to the formula for the quotient rule and substituting all of these sort of different expressions or functions in. Let's do that directly. So my v is x plus 1, right? We can see that directly from here. My du by dx is just 1. The minus sign has to come along. The u, it's just x. We see that there. So it's just x, and my dv by dx is of course just 1, and then the whole thing is over v squared, but my v is x plus 1. So it's all over x plus 1 squared, okay? So so we have that. Now we can just tidy this up a little bit. So the numerator is just x plus 1 take away x, and the denominator is just x plus 1 all squared. And at this stage, we see that the x's in the numerator are going to cancel. So in fact, we've managed to work out our derivative, and our derivative is nothing other than 1 over x plus 1 all squared. Okay? So here's the remark I actually wanted to make. We can actually do a check. It will just take a little bit more of thinking in being able to manipulate our expression in a form where we can differentiate it. So let me rewrite the function down, which I've done here, and now what I'm going to do is re-express the numerator in a slightly interesting way. I'm going to add 1, and then I'm going to take away 1. Okay? So the point of adding and taking away 1 is collectively this thing here is 0. So the entire numerator here is the exact same thing as the numerator here. So this equal sign is perfectly well defined. Okay? So once we've got that, now I can start to massage this and say I'm going to split the thing up by keeping that together and then keeping that as a separate thing in itself, right? So I'm going to have plus minus 1 over x plus 1. But of course, the beauty of doing that is that here I have the same numerator and denominator. So I can simplify that further to say that's just going to give me 1, and the plus and the minus is just going to give me minus, and then I'm just going to have x plus 1. So at this stage, what we can actually do is differentiate this directly, okay? Because we can certainly differentiate this term, and we should be able to differentiate this because we can differentiate the top and we can differentiate the bottom, right? So let's do that. So dy by dx is just going to be the derivative of everything on the right hand side. I'm just going to write it in a slightly funky way. X plus 1. This is going to be the derivative of everything on the right hand side. So I've just basically differentiated this side and that side. I should say minus, not quite plus. But obviously when we know that when we differentiate something like that altogether, we can differentiate each term. So I can just write that out. So I can differentiate the 1, and then I can differentiate the minus just comes along for the ride, and I can differentiate 1 over x plus 1. Okay? So once I've got this, now I've got to differentiate the function 1 with respect to x, and we know what that's going to give us, because every constant function differentiated gives us 0. And then we've got to differentiate the function 1 over x plus 1, right? Uh, at this stage, you can actually use the quotient rule again. For the purposes of time, I won't do that. What I will do is I'll just write down what the answer is going to be. You should get just minus 1 x plus 1 to the power minus 2, right? But of course, there was a minus sign, which was on the outside because of this thing here. So that's that minus sign. So when I have the two minus signs I've got, this one and this one, they combine to give me a plus sign, x plus 1 to the minus 2, which is a positive, obviously. In other words, that's the same thing as 1 over x plus 1 to the 2. So example 5, we're greeted with a slightly more tricky looking function. The interesting thing to notice here is the denominator is e to the x, in fact. And because the denominator is e to the x, then we know that it's never going to be 0 because e to the x is asymptotic to the x-axis. So in fact, the function is defined for every single x as an input, which means the derivative we're going to work out is also well defined for every single x as input. So let's work out the derivative. We go back to using Newtonian notation. So I'm going to have capital F is lowercase f over lowercase g, where my lowercase f is x and my lowercase g is e to the x, right? So let's write down the sort of formula for the quotient rule. So I know I'm going to start with my function, which is in the denominator, if I can only write it down. So it's going to be gx f prime x minus fx g prime x, and the whole thing is over g entirely squared, right? So again, as before, we're going to need derivatives of f and g. Since we have f and g, let's work out their derivatives. F differentiates to give me just 1 because f is just x, and x differentiates to give me 1 with respect to x. And g is an exponential, and we know e to the x differentiates to give us e to the x, right? So when we have that, I can go back to my formula for the quotient rule and just put things in, quite frankly. So my g is e to the x, my f prime is 1, my f is x, my g prime is e to the x, and the denominator is g, which is e to the x, but I'm going to square everything. So we've basically got a solution for our derivative. The only thing that's left to do is to just tidy this up a little bit, which we can sort of do now. Let's uh, let's do that. So we're going to say the numerator is just going to be e to the x minus x e to the x, and the denominator is obviously just going to be e to the 2x. But we can sort of factorize out an e to the x from the numerator, and the denominator is just going to be e to the 2x. And at this stage, because we have same sort of base, we can start to combine this to say, well, okay, it's going to be 1 minus x, and it's going to be e to the x minus 2x, which of course is nothing other than 1 minus x e to the minus x. So we've actually worked out our derivative. So just because there's no easy way to check the answer, it doesn't mean there's no way to check the answer. In fact, what we could do, if you really wanted, you could take a look at this function here as x over e to the x, and you can say, let me write that down as x e to the minus x, right? And now I could go and apply the product rule to this, okay? Because we can take that to be, say, one of our functions. So let's just say f of x, and we can take this one to be the other function, g of x, and we know that f prime x is f of x g prime x, let me write that down, plus g of x f prime x. Okay, that's the product rule. We did a lot of this in the previous video. So if you're not sure about this, just please go take a look at that. So I can write down my derivative of capital F in this case by basically differentiating the g, which is going to be minus e to the minus x, and multiplying that by f, which is just x, and then adding on my g, which is e to the minus x, and multiplying by the derivative of f, which is just 1, right? And when I sort of factorize my e to the minus x from here and here, what I actually end up with is minus x plus 1 e to the minus x, which of course is exactly the same as 1 minus x e to the minus x. So indeed, our solution here is completely correct, right? I should make clear, it is clear from the context, the lowercase f here is not the same as the lowercase f here, right? So I've sort of redefined my f, and I've redefined my g. So in this case, we encounter a trig function as part of our quotient. So let's try and differentiate this. So I'm going to use Leibniz notation again. So in this case, we're going to try and have u being the numerator we've already got, which of course is sine x. So I'm going to say u is my sine x, and v therefore has to be the denominator, which is just x. And of course, given how it's defined, then x should not be 0, because otherwise we start to run into problems. So let's write down the quotient rule. The quotient rule in this case is just going to be, I start with v, and then I sort of write down standard things. So du by dx minus u dv by dx, and then the whole thing is over v squared. So I need derivatives of u and v. So let's differentiate u. We know that the derivative of the sine function is the cosine function, and we know that the derivative of x is just 1. So I come here now to the formula for the quotient rule, and I say, okay, well, my v is just x, so I write the v down, and then I say my du by dx is actually cosine x, so I write that down. And then the minus is just there, and the u is sine x, so I write that down. And the dv by dx is actually just the 1, so when I multiply sine x by 1, I just get sine x, so I'm just going to leave that alone. And then lastly, the denominator is going to be v squared, which is just x squared, so I write that down. And here we have it. We actually already have our function in as simple a form as we can write down. And so I'm just going to rewrite it, although there's no need to, but this is it. So we've actually worked out the derivative. Of course, this is not valid for x equals 0, so x should not be 0. So the only remark might be no easy way of checking this. So no easy way of checking this. But you may, of course, use the product rule again in this case. So I can go back and say sine x over x can actually be written as x to the minus 1 sine x. And if I just quickly run through the product rule, I write down the first function, I differentiate the second one, so sine differentiates to give me cos. I write down the second function, which is sine, and I differentiate the first one, so minus x to the minus 1, so I differentiate to give me minus x to the minus 2. So if I just simplify this, I get cos x over x, and I get minus sine x over x squared. And of course, combining this into a single denominator, I get x cos x over x squared minus sine x over x squared, which is nothing other than x cos x minus sine x over x squared. So we've actually indeed managed to show that the answer we worked out is the exact same as the answer we got in the other case. And of course, x cannot be 0 in both those cases. So the quotient rule works. So example 7, we again have a quotient, but this time we're going to be working in the Newton notation because we keep swapping between Newton and Leibniz to just make sure that we're all happy with being able to do that. So the quotient now is obviously a polynomial over a trig function. So I'm going to take my lowercase f of x to actually be x squared, and I'm going to take my g of x to be cosine x. So, okay, so once we have that, then I can write down what my quotient rule is. The quotient rule is just g x f prime x minus f of x g prime x, and the whole thing is over g of x squared, all squared. Okay, so we work out our derivative of f and g because we need them in the formula together with what f and g are, but we already know what f and g are, so we just work out f prime and g prime. So f prime is actually going to give me 2x because x squared differentiates to give me 2x, and the cosine function differentiates to give me the minus sine function. We know this, so let's now put all of this into the formula. So my g of x is cosine x, so I start with cosine x, and then my f prime x is of course 2x, so I can see that there, so f prime x is 2x, and then the negative sign is there. My f of x is x squared, which we can obviously see directly here, right? So then I need my g prime, which is minus sine x. So I'm just going to write that down. So minus sine x, and this whole thing is actually over, this whole thing is over sine, no, g of x is cosine. Sorry, so I nearly screwed that up. So g of x is cosine, which is here. So I'm going to say cosine x, and the whole thing is squared. Then simplifying this, the only thing I've got to be careful about is there's a negative here and there's a negative there, and they're going to combine to give me a positive. So I'm just going to end up with 2x cos of x plus x squared sine of x, and then the whole thing is over cos of squared x. And yeah, we can tidy this up a little bit perhaps by factorizing out an x. So we can do this, and then we can say it's going to be 2 cos x plus x sine x, and the whole thing is going to be over cos squared x. But other than that, there is not really much else we can say. Uh, and in this case, as we've sort of said before, we have worked out the answer, of course. As we've said before, the remark would be it's not easy to check the answer. Not easy to check the answer. And in this case, even with the product rule, even with the product rule, right? And why is it not easy to check the answer with the product rule? Because if I rewrite this, what I actually have is I have x squared over cos x. And if I was to, because the way we were using the product rule was to somehow put this denominator up with a suitable power, and then we can basically, in this case, we could say cos x minus 1, and then provided that we can differentiate the first function and the second function, the entire function, then we can use the product rule. But in this case, it's not obvious for now how to differentiate a function like that. We've not seen that, right? So in this case, the quotient rule would be the only way to be able to differentiate the function we started with. In fact, if you were given the function in this form, then for now our best bet would be to convert this from this form into that form and then go use the quotient rule. Okay, so this again highlights the importance of the quotient rule. So example 8, we have another very interesting looking function. It's combining exponentials and trigs in some sense. But what's more interesting about it is, as it stands, I cannot actually directly differentiate the denominator easily. Of course, we could differentiate the denominator because we've got a function there and a function there, which we can differentiate individually. So we could differentiate the entire function here using the product rule. but that would make life a bit harder because to differentiate the entire thing here, because we've got a quotient, we've got to use the quotient rule. So basically, if we did it that way, we would have to combine doing the quotient rule together with the product rule. And if I wrote down a formula for that, that'd be horrible. But even if I did it without doing the formula, it will be very long. So we need to start to use some sort of ingenuity as a way of working around this. So what we're going to do is we're going to re-express our function in a form such that we can apply the quotient rule directly without having to turn to the product rule. Okay, so how are we going to do that? Well, I'm going to first of all write down the function we have, and then I'm going to say we know something about sort of fractions. What we know is if I have a over b over c, then that's basically the same thing as a over bc, right? But the beauty of that is, of course, more often than not, we would go from the star side to the double star side, from the left-hand side to the right-hand side, but you can also go the other way, right? So let's go the other way in this case. So what I'm going to do is I'm going to call my 1 to be a, my e to the x to be b, and my sine x to be c. And I'm going to just basically write this format out. Okay, so my a is 1. Oops, I should change color perhaps. So my a is 1, my b is e to the x, and my c is sine x. So I've now written it like this. That might at first sight look like I've made it more complicated, and in some cases it would be more complicated. However, in this case I can take the 1 over e to the x and rewrite that as e to the minus x. Okay, and then now I've got sine x in the denominator, and this is beautiful because I can differentiate the numerator separately now, and I can differentiate the denominator separately now. So now in this form, I can actually start to apply the quotient rule directly. So I say let y equals u over v, where u is equal to e to the minus x, and v is actually equal to sine x. So again, what's my quotient rule telling me? Well, it tells me the formula that we've seen lots of times now. So v du dx minus u dv dx, and the whole thing is over v squared. But of course, I need to differentiate the u and the v. So I do that now. The derivative of e to the minus x is just minus e to the minus x. We've seen this sort of thing before. And the derivative of sine x is again very familiar to us. Sine differentiates to give us cosine. Okay, so once we have that, we take all of this information about u, v, and their derivatives, and we put them into our formula. So we basically end up with v obviously is sine x, so I say sine x, and then du by dx is minus e to the minus x, and then my u is e to the minus x, and my dv by dx is cos x. And then the whole thing here is over v squared, and my v is sine x, but I have to square everything. Okay, so we have that. So at this stage, it's just going to require a bit of patience to tidy this up. The interesting thing is I've got a minus e to the minus x here and a minus e to the minus x here, so I can take both of them out. So I'll come here and say, let's take out minus e to the minus x. So the numerator then just becomes sine x plus cos x, okay, because we took out all the minuses. And the denominator is just going to be sine squared x, of course. Now at this stage, that's simple enough, I think. So we can sort of leave it there, and that's the answer to the initial function we were trying to differentiate. So lastly, it's worth saying the remark that there's no easy way to check this answer directly. So now that we've seen lots of standard sort of calculations of using the quotient rule, let's look at some sort of slightly more interesting ways of using the quotient rule. So in this case, we're given a function at capital F of x, but the function is a quotient of a quotient. So we've got a fraction over something in itself, right? And as I said in the last example, this slightly silly way of doing this would be to repeatedly apply the quotient rule. So what we want to do is we want to be able to manipulate this to get it to the form where it's sort of a lot more manageable. And again, I'm going to rewrite down the statement I wrote down in the blue last time, which is a over b over c can actually be re-expressed as a over bc, right? Last time we went from the right-hand side to the left-hand side. In this case, we're going to go from the left-hand side to the right-hand side, okay? So when I do that, I'm just going to basically have the numerator is going to be the same because you see the a is the numerator there and it's the numerator there, but the denominator is now going to be combined, right? So I'm just going to have e to the 2x. Perhaps I want to change color and do it in black. So e to the 2x, and then the denominator is going to be 2x times by 7x plus 2. And with that one clean step, we've managed to simplify this to something which is just so much nicer. So the denominator is 14x squared plus 4x. Right, of course, I should have said 7x plus 2 cannot be 0, but also 2x here cannot actually be 0 because we've got, in some sense, we've got two denominators, right? So we've got that denominator, but also that is a denominator of another fraction. So both these conditions have to be true. So all the working we're going to do here is not going to be true for x being either minus 2 over 7 or x being 0. Just keep that in mind. So in this case, we go back to our Newtonian notation. So we've got f of x over g of x, where our f of x is nothing other than e to the 2x, and our g of x is nothing other than 14x squared plus 4x. So the product rule formula, of course, is g of x, f prime x, minus f of x, and then g prime x, and then the whole thing is over g of x squared, right? So we, as always, we need f prime and g prime. We have f and g, so let's use them to work out f prime and g prime. My f prime is a standard exponential, so the derivative is going to be 2e to the 2x, and the g is a standard polynomial, so the derivative is just going to be I differentiate each term. So 14 times 2 is 28x, and 4x differentiated would just give me the 4. Right, so at this stage, we're back with the task of putting things in. So I've got to start with my g, so let me write that down. It's going to be 14x squared plus 4x. Let me keep some brackets to keep things tidy. And then f prime is, of course, 2e to the 2x. So it's going to give me 2e to the 2x, and then I have a minus on the outside. And then I've got to write down my f, which is e to the 2x, so e to the 2x, and then finally I've got to write down my g prime, which is 28x plus 4. So I write that down, 28x plus 4, and the whole thing is over my denominator g squared. So I write down the denominator, which is going to be g, which is going to be 14x squared plus 4x, and then it's going to be squared. So now it's just a matter of tidying this up, as we've been doing all this time. So let's first of all factorize out the e to the 2x, because we've got two of those. So let's write that here. So we end up with the 14x squared plus 4x times by 2, because there was a 2 there already, take away 28x plus 4, but then we've got e to the 2x taken out. And the denominator, perhaps we can tidy it up slightly by saying, well, that's already quite messy. Let's rewrite it in a slightly nicer form. What could I do? I could take out a 2 from here and an x from here and a 2 from here and an x from here. So in fact, what I get is I get 2x, and the factorization obviously gives me 7x plus 2, right? And the whole thing is squared, which is reassuring because that's what we started with. Our g was actually in the form 2x times by 7x plus 2, so we've got 2x times by 7x plus 2. So now we continue tidying this up. So let's expand this sort of bracket, and then we're going to get sort of 28x squared plus 8x minus 28x minus 4, and obviously the e to the 2x is on the outside, and the denominator, let's expand that power so it applies to both that and the term in the bracket. So 2x squared all squared is going to give me 4x squared, and then the bracket is just going to be entirely squared by itself. Right, so once we have that, we are nearly done because we see that there's only one x squared term here. I've got two x terms, so they're the only ones that need combining, and then everything else is already simplified. So I'm going to have 28x squared minus 20x minus 4, but of course the denominator is just going to be 4x squared 7x plus 2 all squared. Okay, so we've basically worked out the answer. Of course, it's worth mentioning the remark that actually, if we did not have the quotient rule, there is no other easy way of being able to differentiate a function like this. So there's no easy way to check this otherwise, right? So we have example 10. Given the length of the video, I thought it's probably better just to sort of give a summary of this example, and perhaps you can take some time to sort of sit down and work through this in detail. So what we actually have is we have a function which is obviously the sort of function we've seen before where it's a quotient, but it's a quotient of a quotient. And I just wanted to emphasize the importance of actually doing this the right sort of way, which makes life so much easier. So method one is doing the calculation where it's basically taking that quotient and it's simplifying it into a much nicer quotient, and then it's just applying the quotient rule once. So we simplify, then we apply the quotient rule. And it's a fairly straightforward calculation. You can sort of do it in Leibniz notation. You can, once you've simplified your y, you can take your u to be e to the x, and you can take your v to be x. And of course, I should say x cannot be 0 here because it's not defined. The function y is not defined for it. So then you can apply the quotient rule and you get your du and your dv, you put it into the formula and you basically end up with your derivative. Whereas if you did it the other way, where you said, okay, let me just do it by brute force, by method 2, which is just apply the quotient rule repeatedly, which is you say, I take my u over v, and my u is just the entire thing on the top there, right? And then my v is just the entire thing on the bottom there. So we have these things, but then to work out your du dx and your dv dx, you have to apply the quotient rule to this thing in itself, and you've got to apply the quotient rule to that thing in itself, right? Once you've done that, if you work through it, you'll find that you'll get this as your derivative for u, and you'll get this for your derivative of v. And of course, at this stage, you've got to go back and put u, v, du, dx, and dv dx into the formula for the quotient rule. And when you do that, you actually end up with this monstrosity here, which when you simplify it and work through it, you should get the same answer as that. Okay, so I hope you found this example at least useful in that being able to see that if things are sort of not done in the sort of most elegant way, then sometimes even though you can get the right answer, it can just be so much more work than it would be otherwise. So with that, I'd like to bring this video to an end. If you found this useful, then please hit the like and subscribe buttons. Do let us know in the comments what you would like to see more videos on. Thank you for watching, and we will see you in the next video.